So we took that knowledge that we can use kinetic energy discrimination and we can use shield torch, and we moved to our next generation instrument, the 7500 series. And really, we used the same ideas in the 4500, but we refined them. We designed our ion optics now to work specifically with shield torch conditions, even in hot plasma. We built a collision cell specifically designed to use helium mode and kinetic energy discrimination. And the advantage then was that this type of interference removal was universal. So now we had an instrument that not only worked in the semiconductor industry, but could also be used where you didn't know what was in your sample. For example, the food industry or the environmental industry or the geological industry. So we had a much more universal instrument than we had before. And that allowed the 7500 instruments to be sold in a much broader array of industries. And so we've come a long ways on improving the sensitivity through better ion optics, through the use of shield torch technology. We've come a long way on reducing interferences, but we still had this limitation on matrix tolerance, okay? We were still trying to make an ICP-MS that could analyze the same samples that you might analyze with an ICP-OES. Okay, and so one of the things that we worked on was different ion optic configurations, different lenses, and finally we came up with this idea of doing what we call online aerosol dilution. And so this is an example. This is showing the transfer tube between the spray chamber and the torch, where we can actually add a dilution gas, dilute the density of the aerosol with a dry argon. So we achieve two things. We dry the plasma, or we dry the aerosol going in, and we also reduce the concentration. And the concept sort of works like this, basically. So we're adding a makeup gas, we decrease the density of the aerosol, we actually increase the sample depth, the depth between the end of the torch and the sampler cone. That allows some distribution or some spreading out of the ions, again, to reduce the concentration of the material that gets into the ICP-MS. And our goal was to be able to measure high concentration samples, high TDS samples, for example, like undiluted seawater, which is about 3% dissolved solids. And so this is a 7500 CE instrument, last generation instrument. This is 15 hours of continuous analysis of NAS5, which is a seawater reference material. You can look at the stability for this range of elements from beryllium to uranium. So 15-hour analysis, undiluted seawater, using the technology that I've just shown you. So we've come a long ways on solving that matrix tolerance problem as well. And yet you can see down here, I'll just point to a couple. These are the certified concentrations for the NAS5. These are the measured concentrations, and in most cases we were very, very close to that. So we still have the sensitivity for trace analysis in a very high matrix sample, and that had never been done before with ICP-MS. You can see this is kind of a picture of the skimmer cone after that analysis. There's some sodium chloride built up here, but the opening is still open. So I'm going to just look at this. The next thing we looked at was trying to understand how we could actually increase the robustness of the plasma itself to tolerate high matrix. And we looked at the ratio of oxide formation to robustness of the instrument by looking at cerium oxide to cerium, and we came up with these plots plotting really the oxide, the cerium oxide ratio compared to the sensitivity and counts, and we determined sort of 3 different operating modes for this instrument. One which was very, very high robustness but relatively low sensitivity. This is the kind of conditions we might use to analyze seawater. And then a little bit higher sensitivity system, and then a very high sensitivity system. It might be sort of a semiconductor analysis situation. So, and then we came up with software that would automatically pre-configure those 3 plasma conditions really just at the touch of a button. And all that went into this 3rd generation system, the Agilent 7700. We've got this octapole reaction cell with optimized conditions for helium flow. We can use it with or without the high matrix interface that I just showed you. But we learned one other thing, and that is you can make kinetic energy discrimination even more efficient if you can increase the energy of the ions going into the cell without increasing the energy distribution. And if you can make that ion energy high enough, then you can reduce polyatomics through another mechanism besides kinetic energy discrimination, and that's called CID, or collisionally induced dissociation, and it's very simple. This is a polyatomic interferon, argon dimer. If it's going fast enough and it collides with the helium molecule, we can actually break it apart if this bond energy is low enough. And this is just sort of giving you an idea. Our normal collision cell on the previous generation instrument had relatively low collision energy. It was about, say, less than an electron volt. And in this case, the bond energy of argon dimer is about 1.3 electron volts. So you wouldn't get collision dissociation. If we increase the energy, the ion energy going into the cell to about 100 electron volts, then our collisional energy is higher than the bond energy, and we can actually cause this to happen. So now we've got helium acting in two different modes. So we put that all together again. We came up with a little bit smaller, significantly more sensitive instrument called the 7500 instrument. And this was the first time that ICP-MS had finally become absolutely routine for high matrix applications, push button high matrix applications. And I'll just show you, this is almost going to be a presentation with notes, but I really couldn't do that. This is an example of comparing the performance of high energy or high energy collision mode with the previous version, looking at one of those problematic elements, iron, remember, which was a problem for the semiconductor people. We've been able to reduce our iron background equivalent concentration about 10 times, from about 10 ppt to about 1 ppt. Another problematic element is selenium. The previous version instrument detection limits for selenium were around 200 ppt. Now they're down to about 5 ppt. So again, just much more efficient collision mode using higher energy. So what's next? We've certainly not solved all of those problems, but we've reduced them significantly. We can run much higher TDS samples. We can get rid of polyatomic interferences to a significant level. The instruments are much easier to use. There's still a few problems. Sulfur, phosphorus, those are challenging by quadrupole ICP-MS. They're doable, but they're challenging. Some of the halogens, chlorine is challenging by ICP-MS. So we're looking at now, how can we solve those problems? And some of those problems we've already discussed good solutions to. High resolution certainly can solve those polyatomic problems. It has its compromises. It's capable of very high sensitivity. There are still some interferences that can be resolved by sector field ICP-MSs. They're a little bit more expensive, a little bit more complicated to use, but it's a good possibility. There are other mass spectrometers, time-of-flight mass spectrometers, ion trap mass spectrometers. There's some possibilities there to help solve some of those problems. There are other types of reaction cells available other than helium reaction cells. There are other ionization sources. We've seen some already, glow discharge, microwave plasma, helium plasmas. So there are lots of possibilities. Now, interestingly, Agilent has a relatively strong background in mass spec technology. I'll make one more slide. And so we've got ion trap technology within Agilent. We've got triple quad technology. We've got TOF technology. We've got ion trap technology in other instruments that aren't ICP-MS instruments. So where are we headed? Based on that sort of toolbox of technologies that we've got, what's going to go right here? What will be the next ICP-MS instrument from Agilent? And again, we have ideas, but we want to know what you need. What are your ideas? What are your thoughts? And so we're listening. So please talk to me afterwards. Thank you very much. See you soon.